Welcome to this explainer. Today, we're diving headfirst into a mind-bending story that spans over 2.5 millennia. We are talking about the epic, continuous journey of how humanity figured out the completely invisible building blocks of our universe. We're going to trace the atom, all the way from some incredibly bold ancient philosophy right up to the heavy quantum mechanics that dictate modern chemistry and physics.
So, let's start with a classic thought experiment. If you take a piece of matter and just keep cutting it in half, over and over, can you do that forever? To infinity? Or do you eventually hit a wall, a rigid, unbreakable limit? To really grasp how we answered this, we need to put ourselves right in the shoes of ancient Greek philosophers in the 5th century BCE. Section 1. The Philosophical Atom. Our journey kicks off in an era where the atom wasn't a proven scientific fact at all. It was just a brilliant philosophical guess, completely devoid of any microscopes or lab equipment.
Our historical anchors here are thinkers like Leucippus and his very famous student Democritus. They proposed this Greek word atomos, which literally means uncuttable or indivisible. Using pure logic, they argued that everything in existence was made of these eternal, indestructible little particles, just constantly zooming through an empty void.
And what's crazy fascinating is the sheer logic Democritus used to explain how these particles worked. He assumed that the physical properties we experience every single day were dictated entirely by the physical shapes of these microscopic atoms. He basically envisioned that flowing, splashing water must be made of smooth, round atoms that just easily roll over each other. But on the flip side, a solid, tough piece of iron, that must be made of rough, jagged atoms that physically lock together to form a rigid structure.
Now, you might notice a massive chronological gap between the ancient Greeks and the 19th century. Why the giant wait? Well, you can largely blame Aristotle. He was immensely influential and he flat out rejected the idea of empty space, or the void, which atomism absolutely required. Because of his immense authority, the idea practically stalled for centuries. It took figures like the Roman poet Lucretius to preserve the philosophy, and it really wasn't until the 17th century rise of experimental science that we finally got the tools to actually test these ancient ideas.
Section 2. Dalton's Testable Theory. Fast forward to the 19th century, where an English meteorologist and chemist named John Dalton finally turns those abstract philosophical musings into concrete, mathematical science.
Dalton drops his key postulates right around 1808. He states that matter is, in fact, made of tiny, indivisible atoms, and that atoms of a specific element are totally identical in mass and size. He argued they can't be created or destroyed, which perfectly explained the law of conservation of mass, and that they combine in fixed whole number ratios to form compounds. So the absolute game changer here is that Dalton connected the idea of atoms to measurable chemical quantities and atomic weights. Even though he mistakenly assumed water was just HO instead of H2O, he laid down the mathematical foundation for modern chemistry.
Section 3. Breaking the atom. Because, science loves a good plot twist. And by the late 1800s, Dalton's very first major rule that atoms were completely indivisible was about to be shattered.
See, Dalton, much like Democritus, was convinced atoms were the end of the line, uncuttable. But then, boom, we hit a massive paradigm shift. The discovery of subatomic particles. The supposedly uncuttable atomos was definitively proven to be cuttable, revealing this completely wild, complex internal structure that shocked the scientific world.
Picture this setup. J.J. Thomson had recently discovered the negatively charged electron, and he proposed this plum pudding model, where electrons just sort of floated inside a soft sphere of positive charge. Enter Ernest Rutherford in 1909. He comes up with this incredibly clever gold foil experiment. Using a radioactive source, he fired heavy, positively charged alpha particles straight at a super thin sheet of gold foil. He fully expected them to just tear right through Thomson's soft pudding model and hit the detector screen in the back.
But the results were jaw-dropping. While most particles did pass through, a tiny fraction of them violently bounced backward. Rutherford himself famously said, "It is as if one had fired a large naval shell at a piece of tissue paper and it had bounced back." I mean, can you imagine the shock? This proved the atom isn't soft pudding at all. It has a tiny, impossibly dense, positively charged core right at its center, the nucleus. After that, our understanding just exploded.
Over a few short decades, experimental scientists rapidly mapped out the core internal structure of the atom. You've got Thomson identifying the electron in 1897, Rutherford revealing that heavy nucleus in 1911, and then by 1932, James Chadwick completes the trio by finding the neutral neutron hiding inside the nucleus right alongside the protons.
Section 4. Bohr's orbital model. Now we're in 1915, and the brilliant physicist Niels Bohr steps up to try and create a structured, stable model out of Rutherford's slightly chaotic nucleus and electron discovery.
Bohr lays out some really clear rules. He proposed that negatively charged electrons revolve around the positive nucleus in definite, predictable circular orbits or shells. And critically, each orbit has a fixed amount of energy. An electron that's further away from the nucleus has more energy than one close up. He introduces quantum numbers, n equals 1, 2, 3, which mapped out the KLM shells, and stated that electrons can jump between these levels by gaining or losing specific packets of energy. Basically, they can only orbit stably at very distinct, mathematically fixed distances. Sounds super neat, right? Like a perfect little mini solar system. But there was a catch, a huge one. Bohr's model was highly specific. It basically only worked for hydrogen-like species that contained just one single electron. As scientists built better tools and looked at the spectra of larger, more complex atoms, they found weird anomalies like the Zeeman and Stark effects. They realized really fast that Bohr's simple circular rings were totally inadequate for complex matter. It was time to break the rules all over again. Section 5. Entering the quantum realm. This is our final, mind-bending leap, where we officially leave those neat physical paths behind and cross over into the heavy, abstract math of wave mechanics. Let's talk about the absolute core concept of this modern era, the wave function. Instead of neat planetary orbits, we're now dealing with complex solutions to the Schrödinger equation. These wave functions don't tell us exactly where an electron is. Instead, they describe the probability density of an electron within a 3D region of space. So, the takeaway here is that we traded fixed physical tracks for mathematical probability clouds that just show us where an electron is most likely to be found at any given moment.
Now, to actually map out these complex wave functions mathematically inside a 3D atom, you can't just use a simple flat 2D grid. You need spherical polar coordinates represented by the radius r and the angles theta and phi. This is what allows scientists to pinpoint the precise probability density in the weird balloon-like shapes of these orbitals in 3D space, showing exactly how far from the nucleus an electron might be and the actual angular shape of that space.
And when you run all those complex numbers, the ultimate result is that every single electron inside an atom gets its own, totally unique 4-part address in space. We use the quantum numbers n for the shell, L for the subshell, ML for the orbital, and MS for the electron spin. Take beryllium, for example. Its 4 electrons are neatly filled into these slots, and each one gets a specific spin-up or spin-down configuration. No 2 electrons ever share the exact same set of quantum numbers. It is just a beautifully organized system, all born entirely out of probability.
So, what is the big picture here? Well, the history of the atom proves that science is an unending cycle of refining models and constantly replacing old assumptions. What you really should take away from this explainer is that our grasp of the invisible universe relies entirely on our courage to challenge what we think we know. From Democritus challenging the idea of infinity, to Dalton challenging alchemy, all the way to Rutherford and Bohr challenging Dalton, progress literally only happens when we test the limits of established facts.
As we wrap this explainer up and leave the heavy math of wave functions behind, I want to leave you with this final provocative thought. Did it simply take millennia for the tools of experimental science to finally catch up with the pure insight of ancient philosophy? Think about it. Democritus was essentially right from the very start about there being an uncuttable limit to matter. But humanity needed 2,500 years of advancing technology, relentless experiments, and constant rule-breaking to finally prove it. Thank you so much for joining me on this explainer, and remember to always keep questioning the mechanics of the universe around you